Who just came in? Okay. Get you your test here.
Have you been here recently?
What's your last name? There we go. Okay. All right, so the handout that I just gave you shows the distribution kind of the grades. I combined two graphs into one here, so boy, you can't tell there's supposed to be different shaded regions to separate the quartiles. But I think you can read this and see enough. The highest grade in the class was a 104. And the reason why it's 104 is because remember that in-class quiz I gave? And then I said, forget it, we'll count this as bonus. That wound up being the bonus problem. So highest grade was 104, which I believe was a perfect exam with a correct answer on the bonus, okay? 11 A's, no B's. No B's. C, 1 C, 4 D's, and 10 F's. And you can kind of see from the chart, you know, there were some D's that were kind of close to C's, and then it just kind of dropped off at the end there. So the average was a 70.4. Standard deviation was 27 points, which means what? What is standard deviation basically telling me? It's like a plus or minus. It's basically the spread of the grades. The larger the standard deviation, the more spread out everyone is. And 27 is a huge standard deviation. So it looks to me like if you just look at this bar graph right here, 11 and then 10 on the other end, I mean, it kind of looks like this or this. There's not a whole lot of in between here, right? I thought that it would be also worth it because I looked at everyone's work as far as like, you know, how clean your work was, how easy it was to read, you know, neatness. And I have an example of what I consider to be very, very, very good work. And I'm going to hand this out. I've already asked the student if I can do this. It does not have their name on it. And if I didn't use yours, don't feel offended because there were several of you who had really, really good work. But this particular work, I'll point it out once you get a copy. I'll point out what it is that makes this so unique. Okay, so go ahead, take some, pass these around. Now, they're not in order, okay? I was having a fight with the copier. They didn't want to put things in the proper order. But let me let everyone get a copy and then I'll talk about it. I really don't want to eat too much time here. Everybody have a copy? Look at the page that has like half blank and then it has number 1. When you look at this work, okay, I don't think there's any question as to what's being done. Like everything is neat. It's actually numbered 1, 2, 3. So my eye, when I'm grading this, is going to follow. I'm going to look at number 1, number 2, number 3. That probably means the 3 different vectors. I don't know. But there's no question what the answer is, right? It's boxed. It's nice and neat, right? So maybe you don't have this neat handwriting, but that's not what it's about. Let's flip that page over. Go to number 2. Again, everything's neat. Look, they even wrote A, B, and C because there were 3 parts of the problem, A, B, and C. Very easy for me to see where to look, right? Drew their own pictures for each one of those. The sphere problem next to it, it's broken up into 3 different sections. First, the point of intersection, then the equation of the sphere, and then the very end, the vector equation of the line. I mean, that's very nice, easy for someone to read. Go to number 5, which is the tetrahedron. Notice on the picture of the tetrahedron that they actually labeled the tetrahedron A, B, C, and D, and they actually put the points there. So there's no question as to what's what. I saw a lot of people, they said A, B, C, D, but then when I went to go look at a picture, there was no A, B, C. So I don't know what your A, B, C, D is, you know? So, I mean, there's nothing assumed in this. Everything is in detail. Let's see, there was another one, the parallelepiped one. Again, on the parallelepiped one, number 4, the sides are all labeled. So I just wanted you to see an example of what I consider to be where you want to go with it, just organizing your ideas. The neatness is also a plus, but it's not necessarily, I didn't have great handwriting when I was back in calculus, so, but get the ideas down clearly, all right? I hope that helps you. And what I'm going to do is, I'm going to try and maybe, I gave this person a bonus for this, okay? For it being so clean and for me being able to use it. On the next mini exam, I will pick another one, but it won't be that person. Unfortunately, we have to share the wealth here. So I will pick another person for neatness, and so that way, hopefully, 8 people will get bonus for improving on their work. All right, let's get going. We have a lot to do today. If you have any questions over the mini exam, everything I handed to you, those are all the correct answers. So you now have kind of a key for the exam. We left off last time talking about the derivatives of vector functions. And then we got to this point where we're going to have a bunch of rules. I'm going to run through these very quickly. If you have 2 vector functions, so these are vector functions. You know how we've been using R? Let's say instead of R we use U and V as 2 vector functions. Let's say that they're differentiable. So you can take the derivatives of them. C is a constant, and F is a real valued function. So F would be something like sine of x, or x squared, or e to the x. Then here are all the different properties that we have for vector functions. The first one, if we take the derivative of the sum of 2 vector functions, you can take the derivative of each one separately. That's just like in Cal 1, isn't it? If you take the derivative of a constant times a vector function, now what type of multiplication is this right here? That's scalar multiplication. You're allowed to just pull the constant out and take the derivative of the vector function, just like in Cal 1. So scalars come along for the ride, right? Now this one's a little weird. You have the derivative of a, what is f of t compared to u of t here? This is a function which we call a scalar function because it's not a vector function. So this is like e to the x times a vector function which has the angled brackets, right? You have like 2 or 3 components to each one of these. If you want to take the derivative of that, it's kind of like a product rule. You see it? It's the derivative of the scalar function times the vector function plus the scalar function times the derivative of the vector function. So isn't that just like product rule? Yeah. Just keep in mind, though, this derivative is a derivative of a scalar function as opposed to this, which is derivative of the actual vector function. So you have to do each component. I'm about to use this property here in just a second. This one. If you take the derivative of 2 vector functions dot product, so if you dot 2 vector functions together and take the derivative, then you get product rule again, isn't it? But instead of multiplication, these are what? Dots. And we have the same exact thing for cross products. If you would want to take the derivative of the cross product of 2 functions, then it's basically the product rule, but we're replacing product with cross product. Understand? And then the last one is a chain rule. If you take a vector function and inside of it you plug in a function and you want to take the derivative, what you do is you take the derivative of the vector function, and inside of it you place the scalar function and then multiply that times the derivative of the scalar function. So just know that these are all here. We might need to refer back to them. All right. We're going to do this problem on the board. Show that if r of t is cosine t sine t, then r of t is orthogonal to r prime of t for all t. What does this draw? Unit circle? Two-dimensional or three-dimensional? Two-dimensional, right? This is going to be a two-dimensional curve. It's actually this. And what we're trying to show is that r of t, which would be some vector, right? R of t is a vector. If I plug in a t, it's a vector, isn't it? Like if I plug in 0, won't I get a vector? I plug in pi over 4, a vector. So r of t is some vector that comes from the origin out. I want to show that that vector is orthogonal to its derivative at that point. So if I draw the derivative is tangent to the circle, isn't it? I want to show that that's orthogonal. So who wants to volunteer to tell me how you would show that something's orthogonal? What would you do if you wanted to show something was orthogonal? Dot product, right? So really what this comes down to is this. I want to show, WTS, I want to show that R dotted with its own derivative is 0 for every t. Do you agree if I show that, then I've done this? Okay, so let's take r of t, which is cosine t sine t, and let's dot it with its derivative. What's the derivative of this? Negative sine t times cosine t. I'm going to run out of room over there, so I'm going to move here. Cosine t sine t. I'm dotting that with negative sine t cosine t. And we need that to be 0, right? So what do you get when you dot this? Cosine t times negative sine t, which is negative cosine t sine t. Plus, now we do this times this. Sine t times cosine t. And that is 0. Check. They cancel out, right? So it's orthogonal. So if you draw that vector that goes from the origin out to your curve, and then you look at the tangent vector to the curve, guaranteed those are always going to be orthogonal to each other for this particular function, for this curve. Questions? There's the picture of it, of what's happening. If I let t move around, right, this is the tangent vector. Here's your tangent vector. Here's the vector function vector. And if I start letting time elapse, it draws the circle, right? The black one's drawing the circle. The red one is just the tangent at all the points, and just notice that it always stays orthogonal to the black one. This is a weird problem right here. Show that if, what? The magnitude of a vector function is a constant, then again, the vector function is always orthogonal to its derivative. So can anyone tell me what this would look like if I asked you to draw a vector function that had that property? Can someone explain like what that might look like?
Maybe a line.
I'm saying like geometrically, like picture-wise, what is it going to look like?
Or it would depend on the 3D or 3D.
What do you want? Either one, I don't care.
2 would be a point, or line.
2 would be a line. I've heard line a couple of times. Let me draw a line here. Okay, let me show you a couple of vectors that this line would draw. It would draw the vector that goes from here to here, right? The vector that goes here to here. It's all the vectors that put all those together, right? Does this satisfy this condition? What does this condition say? The length of the vector function at any point in time must be constant. Are these vectors, do they have the same length? It's not constant. So it can't be a line. Do you all see that? A point would be basically the zero vector, right? So I guess that could qualify, but then C would be 0. Circle? Would a circle work in two-dimensional space? If I draw vectors going out to any point on the circle, are they always going to have the same length? Absolutely. Isn't this problem almost like the problem I just asked you? In the previous problem, I gave you a circle, didn't I? And we showed that this was true? Now what we're doing is we're expanding on that. Maybe we don't need it to be just a circle. Maybe this is the only condition we need. So I agree. This is what it would look like in two-dimensional space. But how about in three-dimensional space? And don't jump to an answer yet. Think about it first. You jumped. Why can't it be a sphere?
Can't be negative.
No. What did we talk about? Vector functions draw what? Curves. A sphere is a surface. But you're on the right track. It's any curve that lives on a sphere. Right? So imagine it's almost like, let's say I'm the origin. Okay, I'm holding at the origin. Here's the origin. And I attach a string to a ball. And somehow I start waving this thing around without moving here. Just imagine that ball moving around, but it's stuck to the origin. It's trying to run away, but it's stuck. So it's stuck on a sphere, isn't it? It's not going to draw the whole sphere, but it's stuck. And so the distance from the origin to that curve is always the same, isn't it? So in 2D, it has to be a circle. But in 3D, it can be any curve that lives on a sphere. We want to show that the vector function is orthogonal to its own derivative. The way I'm going to show this is not natural at all right? Let me see if I can remember how to do it. Oh, okay. So watch. Check this out. Again, you would not come up with this on your own, but it's a nice application of how we can use properties of dot products and things like that to actually show, to prove a theorem. Anyone who's a math major, you'll appreciate the fact that the way you get to this answer is not obvious, and this is what math people have to do. They have to think of other ways to prove things. So tell me if you agree with this. God, these markers suck. I just pulled them out of a brand new box, too. Take the vector function and dot it with itself. Do you agree and remember that this was equal to the magnitude of the vector function squared? I'll show it to you in a different way. This is what I showed you. If you take a vector and you dot it with itself, but only with itself, this was equal to the magnitude of u squared. Does that look more familiar? That was a property from way back in dot products. So anytime you dot a vector with itself, you get the magnitude of the vector squared. So if I take this vector function, I dot it with itself, won't I get the magnitude of the vector function squared? Which for us would be what? What are we assuming is true? The magnitude of this vector function is c. So this is c squared. Agreed? Okay, well I still haven't shown what I want to show. What do I want to show? I should have put that up here. What do I want to show? I want to show that r dotted with its own derivative is 0, right? That's what I want to show? I mean, I'm very disappointed in these markers. Agreed? That's what I want to show? And I've shown you that this is true, and you're like, so what, right? Who cares, right? So what I'd like to do now is just rewrite this. You know, I'll do a little different. I won't rewrite this. Just tell me what that is. So this is a separate line of thought here. Here we've got that. We understand that. We agree on that. What is the derivative of the dot product. And you may be saying, why are you doing that? Just watch. Can I take the derivative of the dot product of two vectors? Yes, I just gave you the property just a second ago, didn't I? And it was like a product rule. It would be what, like the derivative of that one dotted with what? This one plus the derivative of the second one dotted with the first one. Now, do you see why I did that? What I'm trying to show, right, isn't that this? Isn't that this? Yes? Now, put this side together. That's two of them, right? Since they're the same thing? Who's going to tell me what the left side of this equation is? Like, if I'm looking at this as an equation, this derivative, right, is this. Maybe I shouldn't look at it like an equation. I think that would be too confusing. We agree with this. Yes? We're okay? Okay. But can anyone tell me what this should be?
0.
Why?
Because
He said 0.
the vector function dotted with itself.
This times dotted with this is what? A constant squared. What's the derivative of any constant squared? 0. So this has to be 0, doesn't it? So, therefore, 3 dots is therefore. Therefore, 2 r prime t dotted with r t must be 0. Divide by 2, both sides. If you divide by 2, what do you get? What you want to show. And we're done. Is that weird or what? That seems strange? So, see, when you look at like a proof of something, this isn't really a proof because that's not really a theorem necessarily. When you look at someone's work that shows that something is true, sometimes you'll look at it and you'll be like, yeah, that's obvious. I can see exactly why they did that. But then there's other things like this where it's like, well, why did they do that? Like, who showed them to do that? And that's the challenge for mathematicians, is to have something that they have to show, and the way you do it is not necessarily like just following a trail. Sometimes you have to come in through the back door and figure out another way to attack the problem. This is a perfect example of that. Okay, we're moving on. Okay, so we're now going to focus on some applications of derivative functions, of derivatives of vector functions. I'm gonna blow through this pretty quickly. I want you to look at two vector functions, which I'm calling R1 of t and R2 of t. R1 of t is t squared. The other one is t squared t to the fourth. All right? I'm going to show right now that, just by convincing you with a picture, I'm not going to go through this whole example. You can do that on your own if you'd like. I'm just going to show you the picture. It's too big. There we go. So we're having a little comparison. Here's R1 of t. Here's R2 of t. I've had the computer graph them for me. Do they look to you to draw the same exact curve? Do they draw the same curve? It looks like it, right? And I'm going to tell you, yes, it is true. They will draw the exact same curve. But does that mean that these are the exact same vector functions? So what makes them different, right? Does that seem like a natural question? If they draw the same curve, then how are they different? Let me take you to a point in time. At t is 0, here's where we are. Here's where we are. Look at t is going to be 1 now. Oh, no, it's not. It's going to be 0.25. T is now 1. Do they look like they're at the same place? Yes? Okay, let's let t be 2. Oh, okay, so now something changed, right? This one's here and this one's here. But they're drawing the same curve, aren't they? Now I'm just gonna play it. I don't know why it's flashing. It's kind of weird that it's flashing. Do you see it? Watch what happens to this point. It takes off. This one's moving much slower, isn't it? It's still drawing the same curve, but not as fast. So if you were actually like an ant, a little bug, an ant or something crawling along this curve, this is bug number 1 and this is bug number 2. Bug number 1 is going slower than bug number 2, right? How do we know that by looking at these two? I mean, how can we tell? Well, let me show you their derivatives, and let me back this up. I want you to look at the tangent vectors. What's the obvious difference between those two tangent vectors? One's longer than the other, right? This one's longer than this one. And if I back it up to, remember where they were at the same point at 1? At t equals 1, weren't they at the same place? Yes? But the difference is this one has a vector that's very long compared to this one. They're pointed in the same direction, aren't they? So that derivative vector somehow indicates the velocity, the speed, right, at which this is moving. And that's what we're trying to get at here. The length of this vector compared to the length of this vector matters, right? It's gonna tell us something. I think you get the idea. I have more stuff here. I can compare them at different values. Like I picked some values here. At this point, the length of the vector function is 4.7. Here, it's 2.24. If I go up to this point, it's 8.06. But at the same point over here, it's 32. So this length's bigger than that. So I don't need to show you anymore. Are you comfortable with that? Yeah? Okay. All right, so this is the summary of it. If r of t is a vector function which represents the path of a particle or object through space, and what we mean by that is not stars and moon. Space meaning 2-dimensional space or 3-dimensional space or 4-dimensional space. If r of t is a vector function and we have the path, the curve is a path, then we will call the r of t the position function. The derivative of the velocity or the position function we will call v of t, and it is called the velocity function. This look familiar? In Cal 1 you did this, right? Derivative of position was velocity, derivative of velocity was acceleration. Okay? But there's something different here. When we take the derivative of r, we get a vector function, don't we? Angled brackets, vector function. And so we call this the velocity function. If we look at the magnitude of that derivative, it's a length, isn't it? That's the speed of the particle. So speed and velocity are not the same thing, right? Speed is the length of a vector. Velocity is the actual vector. Vectors have length and direction, don't they? So velocity is very different than speed. They're related, but they're different. And then if we take the second derivative of the position function, we get the acceleration function. The larger the magnitude of the derivative, the faster the particle is moving at that point in time. That's the homework for that section. Okay? Actually, I have more. All right, there's going to be more. But we're going to, that was the homework that coincides to the derivative part of that section. All right, integration. Well, right after differentiation, you have integration, right? So if we have a vector function, 3 components, then the integral, the antiderivative of the vector function from a to b, dt. So the variable that we're integrating with respect to is t, because t is the variable, right? What is this saying we do? How do we integrate a vector function? Integrate each component, right? Which is the way the derivative worked. And we were happy with that, weren't we? So here's an example. Oh man. Let's integrate this from 1 to e. So that means I want to take the integral from 1 to e of e to the t dt. I want to do the integral from 1 to e of t square root of t minus 1 dt. And I want to do the integral from 1 to e of natural log t dt. And this class is not, we're not going to go and let's remember how you do all the different techniques of integration. That's the class you took before this. So I would expect everyone, given enough time, without a computer, could do these by hand. I think some of these are easy though, right? What's the antiderivative of e to the t with respect to t? Itself, e to the t. And then I'm evaluating 1 and e. You all comfortable with this notation? Yes? All right, and then the next one, how would you do that one? Anyone have where are my integral specialists in here? Any integral specialists? Integration by parts? Maybe. That might work.
I wouldn't go that far.
You wouldn't go that far? What would you do?
I would probably take the derivative of what's inside of there.
Here?
Yeah. You know what? Never mind. Don't do that.
Don't do that?
Don't do that. Not a good idea. But I still would.
You should have just said, I'd just do something.
I'd do
Didn't
something.
that's what you said last time, right? Something in there?
Oh, you could do a U sub, right?
Basic U substitution would work on this one. I think. Hold on. Let's see it. Let's do it over here. If I'm trying to integrate t root t minus 1 dt, then I can make a basic substitution. U is t minus 1. And if I do that, see, this is where we all come from different backgrounds when it comes to integration. And there's little subtle differences in the way integration is done from instructor to instructor. So if you don't follow what I'm going to do, the way I notate it, the way I attack these, you have your own way. Good, you have your own way. I'm not here to teach you how to integrate. All right? So I would go du equals dt. And then I would just go about rewriting the whole integral in terms of u. So what can I replace t with? U plus 1. So just take this equation, solve for t. So u plus 1. And then what can I replace square root of t minus 1 with? Square root of u, which I'm going to write instead as u to the half. And then dt, I replace it with du. So that's what that new integral becomes. That's easier to integrate, isn't it? Because you can just pass the u to the half through and then integrate each one term by term. So I'm running out of room. I'll do it up here. We have integral. There's two terms. What are they? U to the 3 halves plus u to the 1/2. And then you find the antiderivative of each one. What is the antiderivative of u to the 3 halves? 2/5 u to the 5 halves? Yes?
Yes, something like that.
Yeah, something like that. 2/5 u to the 5 halves, right? What's u, though? What's u? T minus 1. So t minus 1 to the 5 halves. Then plus, what's the antiderivative of u to the half? 2/3 u to the 3 halves. And I'm evaluating that. I need a little more room here. 1 and e, right? I'm done with this one. I mean, I still have to plug numbers in, but I'm done taking the antiderivative? Okay, now, comma, antiderivative of natural log of t. Don't say 1 over t, please. The antiderivative of natural log of t. You could do that one with integration by parts. Or you could just remember the formula. Anyone remember the formula? ln x minus x. So for us, it'll be t ln t minus t. Evaluated 1e. So from here to here, integration by parts or formula. If you were in MyCal 2, who's in MyCal 2? we derived the formula, didn't we? Like, do you remember that now? I said you could put it on a formula sheet once we derived it? Okay. There we go. Close it off. Angled brackets, vector. We're done. I said, who's in my calculus class? None of my Cal students want to raise their hand. They're like, it wasn't me. It wasn't me. All right, now plug in. Now plug in. So what is this? Plug in e first, right? E to the e. E to the e minus, now plug in 1. E. Right? What's next? Oh, crap. That's ugly, man. E goes in here, E goes in here, right? And then 1, what about when 1 goes in? It's all 0, so I'll just write it out. Okay. 2/5 E minus 1 to, I'm not even, don't get your calculator if that's what you're doing. Don't worry about it. Don't worry about it. This is a numerical result. We'll leave it in its exact form, and we'll be happy. All right, so that's this part, right? And then when we plug in E here, let's see what happens. E times natural log E, what's natural log E? 1, so that's just E, minus E, which is 0. Okay, great. If I plug in 1, natural log of 1 is 0, so that's gone, minus 1. So be plus 1, because remember that was in the subtraction. Very good. So plus 1. All right, that's the answer. Our answer is a vector, isn't it? So if you integrate a vector function from 2 points in time, your answer is going to be a vector. Any questions? So that what this means to you is that all that stuff you did in Cal 2, it will creep up on us here. You will still have to integrate in this class. It'll be expected that you do remember how to do integration by parts. And now the integrals may not be as complicated as they were for you, but they'll still be on the table. All right, so like in class test, I wouldn't give you like some weird partial fraction problem where it's going to take you like 30 minutes to break it all up, and I wouldn't do that. But I would expect you to do some basic integration like this. Is that basic integration to you? I don't know. I guess that depends on you, right? All right, where am I? Okay, look at this one. We start out with the derivative of a vector function. I'm telling you that r prime of t is this. And then I'm telling you that r of 0 is 1, 1, 1. So if this is a particle moving around, I'm giving you its velocity function, right? And then I'm telling you something about its position, right, at time equals 0. But then you're asked to find the original position function. So we have to go backwards, don't we? We have to integrate. So what I want to do is integrate my r prime of t with respect to t. If I do that, that should give me my original position function, shouldn't it? Yes? So let's integrate this. That's going to be a vector, right? Vector. And now integrate each of the component functions. So this one's a lot easier to integrate or not? Well, maybe that last piece. What's the antiderivative of t? 1/2 t squared. Okay. And then e to the t. And then how would you integrate t e to the t d t? Wolfram alpha? No. Ultraviolet minus blue. So integration by parts. Again, depending on how you saw it, The way I do it in my classes is we choose what u is, we choose what dv is. So in this case, u would be t, and dv would be e to the t, dt. And then we go down, take the derivative here, du is dt, and v is e to the t. And then we do the formula for integration by parts, which is uv minus integral v du. Does that look familiar? So what would that be? It'd be t e to the t minus a new integral, which would be v du, so e to the t dt. And the antiderivative of e to the t is just itself. So the antiderivative of this should be t e to the t minus e to the t. What are all of those missing, though?
Plus C.
Plus c, right? Don't we always have a constant on all of these? Like each one of those integrations, I should have said plus c, plus c, plus c, plus c. So what I'm going to do instead, if I may erase this, can I erase this yet? Yeah, okay. Is instead of adding constant, I'm just going to do this. It's a constant vector, right? You could imagine that this vector is actually a three-dimensional vector. It's like C1, C2, C3. And so if I took this vector and I added it to this vector, then I would have 1/2 t squared plus C1. So that would be the constant attached to this one. Then this one would have a C2 and this one would have a C3. Got it? Okay. So that's what R of t is, isn't it? R of t equals this. Now I'd like to nail down what these constants are. So to do that, I'm going to use the given information. I know that R of 0 must be 1, 1, 1, the vector 1, 1, 1. So let's plug 0 into this. What is R of 0? Into my vector function, I get what? 0, 1, negative 1, plus some constant vector, right? Must equal what? 1, 1, 1. Understand what I did there? Now solve for the constant vector. Don't you just subtract both sides right there of that equation? Just subtract. So the constant vector should be the 1, 1, 1 vector minus the 0, 1, negative 1 vector. So it's like you're subtracting both sides of this, which is what? 1, 0, 2? Questions? No? You know what? Let me make sure. Did I press record? I did, right? Yeah. I ordered a new microphone. You know how I wear this ridiculous thing? I ordered a new one. I finally invested in a nice one. So I only did it because the damn little battery case I have to take off every time broke, and so I have a rubber band on here now, and so all right, final answer. R of t is 1/2 t squared, right? Then we had here, I'm going to leave some space, e to the t, and then we had t e to the t minus e to the t, like that, plus our c vector. But our c vector is this. So what I'm going to do is take each of these components and put them in here. So this one will be plus 1, right? This one will be plus 0, and this one will be plus 2. That is the actual position function. We could double check it real quick. If we plug in 0, we better get 1, 1, 1, which I'm sure we will. And if you take the derivative of this, you better get this, which I'm sure you will. Question?
So for every time we don't have definite integral, or like where you go from one point to another, you want us to do that?
Yes, if you're integrating a vector function and you're not given limits on t, then it is an indefinite integral, and you will have like a constant of integration. It'll be a vector of integration, actually. Yeah, a constant vector of integration. All right, we keep going. Applications. So what the heck does it mean, right? Well, if a of t is the acceleration function, right, then the antiderivative is the velocity function. And then, of course, the antiderivative of the velocity would then be the position. So we just did that. There's a way to recover from the acceleration function back to the position. What's the difference between this one and the previous one?
Their component.
Yeah, okay, so that's a different function. But as far as what we have to do, we have to get back all the way to r, but we're starting where? At a, right? I don't think I'm going to work through this one. That's why I'm talking about it. So, but let's talk through it. What we'd first do is integrate this, right? And that would give us v of t. So we would get like integral of r of t dt would give us v of t, and we would be within some constant of integration, right? We would get this constant by using this, what we call initial condition, on v. So then we'd plug in 0 to the v function, then we'd figure out what the c is, just like we just did. Then we have our new v. Then we go back and we integrate that one to get r. Yes?
Should it be R or A?
Where?
Integrate.
Yes, thank you. Did I? Yeah, I don't know why I said that. Thank you, Karen. Karen's always checking my work. I appreciate that. Integrating the a to get v, and then integrate v to get r. Yes or no? Okay, just, yeah, twice of what we just did. Oh, what would you do, though? What would you do if this right here weren't v? What if they gave you something like r of 1 is the vector 2, 3, 5? What would happen then?
We would have C and D.
We would not be able to nail what c is, right, on this first one? So that's okay. We would integrate again. So what would the antiderivative of a constant be? So what's the antiderivative of the C1, C2, C3? What's the antiderivative of it? C1t, C2t, C3t. You see how that would be a little bit different? Okay, so just be careful on that. I'm not asking that here, but I don't even think that shows up in the homework, but that's the way you would do it. Okay, I don't know if that matches up with what I have on your handout sheet, but we're ready to move on. Okay, arc length and curvature. This is more applications of derivatives and integrals. Lots of notes here. Arc length of a vector function. A few little subtleties I have to make sure you understand before you start using this formula. You've got a vector function, r of t. It has two component functions, f of t and g of t. Let's say that that's a two-dimensional curve, right? If t varies from a to b, so it's like you're starting the clock at time equals a, and then it starts drawing the curve, and you stop it at b. That curve lives in two-dimensional space. Then the arc length of the curve is going to be given by this formula. But it's important that you can only traverse the curve one time. I'll give you an example of a two-dimensional curve. This one right here, r of t is cosine t sine t. We know that draws a circle, right? It'll draw the full circle on the interval 0, 2 pi, won't it? That'll draw me a full circle. But if I go from 0 to 4 pi, it's just going to draw me a circle on top of a circle. That means I've traversed the same path twice. This formula will only work if you're traversing that path once. Got it? So it's not going to account for the fact that you've gone over yourself. It'll mess up. The formula will mess up. So we want to be careful that what we're drawing is never overlapping itself. But if it's not overlapping itself, you're traversing the path just one time, then the length of the arc, that means you take that curve off the page and you stretch it out and you get out your ruler and you measure the length of that curve. It is given by this formula. It is the integral from a to b of the magnitude of the derivative of the vector function. And that is it. And that's awesome. Because that means if you can find the derivative of the vector function, which I think you can, derivatives are pretty clean, and then you can find its magnitude, the magnitude of a vector is the square root of all that junk, right? Then you're in business. And why does this work? Do we care? Do we want to know? I mean, why is it working? I'll try and explain without eating up too much time. Let's say we have this curve that lives in two-dimensional space, all right? And I'm going to make it a true curve that's not necessarily even a function of x, right? That's not a function of x? No? So what we're going to do is we're going to imagine we're trying to find just the length of this portion right here. And let's just say like we've zoomed in like a million times. So we're looking at an infinitesimal little portion of the curve. If I can find some way to approximate that length, do you agree that that would be an approximation, a decent approximation of this little arch right here? Yeah? And the further I zoom in, the better my approximation gets? Well, what we do is we can approximate this length with the derivative vector and its length, the length of that black one. So the derivative of it runs tangent, doesn't it? So essentially this integral is saying we're going to take all the little lengths of all of these little tangents on an infinitesimally small little interval. We're going to take all the little lengths of all these little tangents and we're going to add them up. That's what the integral does. It adds them up, right? And the dt here also comes into play with some triangle stuff that we would have to do to make sure we've got a good approximation. Add them all up and that gives you the length of the curve. Now, like I said, that's just a real quick glimpse into it. How many of you in your Cal 2, y'all focused a lot on kind of the geometry of taking something and cutting it up and adding up the pieces? Was that not really made important? Is it important? Okay. I know in my class that's like the one thing I do is make sure that everyone understands that this integral comes from the idea. Let's see. Should I quiz my Cal 2 students, even though they already passed? This integral gives you the area under the curve, right, everyone? But what's really happening here, let's see, Cal 2 students, this f of x really represents what?
The height.
The height of some arbitrary rectangle?
Yes.
And dx represents the width of it. And if you multiply the height times the width, you get the area of that little piece. So this is the area of an infinitesimal rectangle. And then the integral adds them up, infinitely many of them. If you don't have that connection, then this, what I set up here, is going to seem like complete, like, what are you talking about? That's all this is doing. This is adding up arc lengths. It's adding up little derivative tangents the whole way around. Okay. Y'all doing all right? Okay. So let's do an example. Anybody know the answer to this? 12?
What did I just say?
Something, right? Come on, without doing the work, someone tell me the answer to this. 1? Look at what it is. What does it draw? What's the arc length of the unit circle? What's the length of it is the circumference, isn't it? 2 pi? 2 pi r, but r is 1. So the answer should be 2 pi. Let's see if we get 2 pi. So according to what I said, we need to do the integral from where to where? 0 to 2 pi of the magnitude of the derivative, right, of this vector function. Well, let's do that work on the side. What's the derivative? Negative sine t, cosine t, right? What's its magnitude? Square root of, how do you find the magnitude of a vector? Square root of each component squared. Sine squared t plus cosines. Ooh, I like that. Because that's 1, isn't it? Nice. So I'm just integrating 1 dt. What's the antiderivative of 1? T. So this is just t evaluated from 0 to 2 pi, which is 2 pi. Got it? But with this formula, you could actually draw less of it and figure out the arc length, right? So like if I wanted to, let's say I wanted to take, here's my unit circle. What if I only wanted to know like this piece right here? Let's just call this, I don't know, let's call that S. And let's call this in here, this is, let's call that T, kind of like for theta. Then how would this integral change? Okay, the bounds would go from 0 to where?
0 to
Well, I don't know what that angle is, right? But what am I calling it? T. Do y'all understand? Let's call it theta, so maybe it'll make a little more sense. Theta, okay? Because that way you don't mix it up with the variable in there. And then this would change, right, to just be theta. And this would change to be theta. And this answer would change to be theta t, right? In other words, you would have this. S would be equal to theta t, wouldn't it? Y'all follow that? Hold on. No. Sorry. What did I mess up there? Theta goes in for t. So it's just theta. So S would be theta. You might be asking me why I did that. I want to change the problem. That's why I want you to see something. Did you all kind of follow that a little? Okay. What if I have not a unit circle, but a circle with radius r instead? How does my vector function change? R cosine. So we would have r cosine t, r sine t. I should put the r in there. Right? If I wanted to find the length, that length right there, I would still go integral. I'd still go 0 to theta, right? And I'd need to find the magnitude of the derivative of that. So let's do a quick derivative on that one. What's the derivative?